Okay, again we come back again for the second part after I think we are at this point where we looked at the summary of the first part. If this works, okay, yeah, it's working. Alright, so now what we wanted to do next, we wanted to look at some examples, applications of all of these formulae that you know. The only thing that I'm not going to do in class, in here, is an application on these two guys, which I forgot to add one or two questions, but I'll make sure that at least in the tutorial or in the worksheet there will be some questions on that so that you see what what the some of the problems look like. Anyway, so the first question, which we did in class in detail, but I'm going to go over it very quickly. So we have, this is a case where we have a circuit, a voltage source, and we have a combination or capacitors, 4 capacitors, 1, 2, 3, 4. And what he wants first of all the charge on each capacitor, the potential difference across each capacitor, and the potential difference across the point AD. Alright, so in order to do these problems, I suggest we use this table in which we list all the capacitors, 1, 2, 3, 4, the capacitance for each one of them, and then the charge on each one of them, and the voltage drop across each capacitor. This is very important for the simple reason that sometimes knowing, for example, these two guys are in parallel, I know that they have the same charge. So if I somehow find C1 and V1, and from which I can find Q, then I know that these two have the same charge, and so on. So this table is very helpful, and I think later on, if those of you who are doing electrical engineering, you will do this using very nice fancy matrices and things like that. So anyway, so the way we're going to do that, we're going to start by first of all calculating the equivalent capacitance for all of these capacitors, and then from there we're going to work our way back. So let's do that. I'm going to first look at these two capacitors. Okay, C1, these guys are connected in parallel, so 1 over C equivalent will be 1 over C1, 1 over C2, so 1 over 4 plus 1 over 4, 2 over 4, and when you take 1 over that, that will give you 2 microfarads. So the equivalent capacitance for these two guys is 2 microfarads. And now I have this. So now these two guys are connected. Now they're one capacitor. And I'm going to combine these two with this guy, which is simply this combination with C3. And that will give me that. So these guys are in parallel, which is easy. Just add them up. These two is 2. And C3 is 4. So 2 plus 4, that will give me 6 microfarads. So I got all of this combination now is 6 microfarads with 4. So that means these two guys now are connected in parallel, in series. So these guys are connected in series, which means that the equivalent capacitance is equal to 1 over, was it 6? Yeah, 6 and plus 1 over 4. And if you do that, then you find that the equivalent capacitance for the whole circuit is 2.4 microfarads. So the equivalent capacitor is equal to, that means what? That means Q, let me get the pen here. Q is equal to CV. This V is 28 volts, right? So from here I can find Q 1, 2, 3, the total 1, 2, 3, 4 is equal to C total multiplied by V, which is 2.4 multiplied by 28. That gives me 67 microfarads. 67, that's the total charge on the combination. But if I go back one step, this combination is simply the combination of C4 plus C123, which are connected in series. In series, that means the charge on this guy is the same as the charge on this guy. So that means C4 has a charge of 67.4, and the combination of these guys has also a charge of 67.2. All right. So now if I go back to my table in the first page, that means I got C4, I got V4, and I got a Q4. Sorry, I got Q4 and I got C4, from which I can find V4. But remember, since these guys are connected in series, that means the voltage, which is equal to 28, is divided among these two. So if this one, now next, so the voltage across V123 is equal to, so the voltage is this 16.8, and the total voltage is 28. That means the voltage across these guys, the top combination, is 28 minus this, which is 11.2. So 11.2, that means, and I know their total charge. So what does that mean? That means this guy, this combination with C12, that has the voltage across here is 11.2, and this guy here is 11.2 because they are connected in parallel. So from here, if I know C3 and I know V3, so that means I can get Q3, right? And what am I left with? I'm left with, I know the total charge on these guys is 67.2. Okay, so once I knew the voltage here, I can calculate Q here, which will be the same for both of them. So V3 is equal to that, 11.2, and Q3, this Q3 here, I found it, which is simply C3V3, 44.8. And not only that, but I also can find the Q on these guys, which is simply 2, the combination of them multiplied by 11.2, that's 22.4. And I know that Q is the same for both these guys because they are connected in series. So Q1 is equal to Q2 is equal to 24, and therefore my problem is solved, and I can calculate V1, V2, and from there I can get all of these Q1, Q2, Q3, V1, V2, V3, V4, and I can go back and I fill out my table. And there are some comments here that I should make. Here that first of all, this Q here, which is Q on C4, should be the same as Q on all of these guys. Okay, so that means if you add these two, that should give you the same number as this one. Okay, and the voltage here, the voltage across here, it should be the sum of these two guys, right? This is the voltage. These two, which is 11.2 plus that. These two should give me 28, which is the voltage is 28 here, and then 11.2 is the sum of these two guys because it's split between them in here. So because 11.2 is equal to 11.2, this here 11.2, here 11.2, but it's split between the two because they are equal. So there are a lot of things that you can actually extract or find out once you do the calculations. The only thing that we did not do here is find the potential difference across the points A and D, that you can easily now do once you have the capacitors. You have C and Q in all of them. Q is equal to CV, or V is equal to C over V. And from there you can find the charge, or the voltage drop across that. Okay, example number 2, which we've done, or example number 7, which we've done in class. So again, you just need to do the calculations as we did before, and we've done this very in detail in class. Example number 8, he wants you to find the charge on each capacitor, okay, and the potential difference across each capacitor. That's very straightforward. Yeah. So he gave you C1, C2, and he gave you the potential difference between these guys. So these guys are connected in parallel. So that means C1 plus C2. And then from there you can calculate the remainder of the question. All right. Now, what I want to do in this example, number 9, we wanted to look at the effect of connecting in parallel and connecting in series. So if I take these two capacitors, one time I'm going to connect them in parallel, and one other time I'm going to connect them in series, and then I want to see the effect. Okay. So when they are connected in parallel, I should make sure I mention that. So this is connected in parallel. So that means C1 plus C2. 4, so the capacitance, the equivalent capacitance is equal to 8. And the energy stored in here is equal to a half CV, which is 288 joules. Now, if I go to when they are connected in series, the equivalent capacitance, remember here it's 8, and here is only 2. And the energy is reduced also to 144. So that's one thing that you should notice, that when you connect in series, it's you increase the capacitance. If you connect in parallel, you reduce the capacitance. The energy stored will be more if you connect in parallel than if you connect in series. Okay. Now repeat the calculations if you insert a dielectric material that has a dielectric constant of 2. What happens? The equivalent C equivalent will be remember, C will be increased by kappa, so kappa times C1, kappa times C2. So introducing a dielectric in between the capacitance here, that will have the effect of increasing the capacitance from 8 to 16. Okay, just simply as you said, it's 2 multiplied by that, because the kappa is 2. And what happens to the energy? The energy now is increased. Remember, I have a V, and now it's 16, here is 18. So the energy increased from 288 to 1152 joules. Again, the same thing if I have so remember, this is in series, so the capacitance is increased from 2 to 4, and the energy is increased from 144 to 88. All right. So that's the effect of introducing a dielectric material, increases the capacitance and also increases the energy or the potential energy stored in the capacitance, or in the capacitor. Example number 11. What is the area of a 1 farad capacitor that has a plate separation of 1 millimeter? If you do that, C is equal to epsilon A over D. D is the separation between the plates, which is 1 millimeter, 0.001. If you do that, you find the area to be something that is, if you think of a square, that will be something like about 10 kilometers of size, 10 kilometers, which is impossible. That's experimentally impossible. How do we overcome that? So this is impractical. Now what we can do that is by simply introducing a dielectric material in between the plates, and therefore we can have a very small, tiny, reasonable capacitor with a dielectric material that has very high K. Therefore we going to, or producing a capacitor that has, or of 1 farad. All right. Example number 12. We have a parallel plate capacitor consists of 2 plates with a total surface area. So this is the surface area. What will be the capacitance in picofarads of the capacitor if the plates are separated by 0.2? The separation is 0, so D is 0.2. And the dielectric medium used is A. Remember, A has a kappa of equal to 1. Repeat the calculations if half the space between the plates is filled with paper, 3.7, and calculate the energy stored and so forth. Okay, so first we calculate the capacitance. The separation is 0.02 in meters. That will give me a capacitance of 44 picofarads, and that also give me the energy stored is 11,616 times 10 to the minus 27 joules. That's the amount of energy stored. And if I introduce the dielectric material, except that I forgot to divide by half, so I apologize, because here I assume that the full space is, I forgot to do that, and I think you can do that as homework here. I forgot to, I thought the calculations, I repeat the calculation with the whole space is filled with the dielectric material. In fact, it's only half. So what does that mean? That means what you're going to have to do. So what I've done here, the calculation is that I'm assuming the whole space is with the dielectric material, is inserted dielectric material. But anyway, so I'll show you how to do it when it's only half of it is filled with the dielectric material. So once we calculate C, okay, then next we calculate the energy stored, which we found to be 159, because now we have introduced the electric material, so the energy stored, we can store more energy. And if we compare, we see that the difference, or not the difference, but the ratio between C0 is a 3.7, which is kappa, which means that C is equal to 3.7 C0. And if we look at here, U over U0, which is 14 U0, which is simply kappa square. It's 3.7. It's around 4, so 16. 3.7 square is 14 U0. Now, let me very quickly tell you how you can do this when it's only half. When it's only half, that means what? That means I have something like this. Half of it is air, and half of it is so this will look like something like this: two capacitors connected in parallel. Okay, one of them has a dielectric so they're connected in parallel, so it will be C equivalent will be equals to C1 plus C2, and the area will be a half, so I have to calculate the C for each one of them is a half the area, and in here I have to multiply by kappa, the dielectric constant. So it's very easy, but you should be able to do it, and if you have difficulty with it, then you can ask me during the office hour or before or after class. Okay, example number 13. We have, again, we started doing this in class, and I think it's better we finish it here in this video. So what I have here, I have an unconducting slab T. So this is a dielectric material that has thickness T, and it has a dielectric constant kappa, and inserted between the plates in such that it's somewhere, not necessarily halfway between the plates, but it's filling the gap or filling part of the gap in between the plates. What does he want? He wants the slabs. What is the capacitance of the system? And he is asking you to use delta V is equal to minus ED, or delta V is equal to ED if you want the absolute value. So remember, if you look at this here, we have the electric field E0 here, E0 here, and in here it's ED, which is E0 divided by kappa. All right, so let's put that in here. The delta V is equal to E, the electric field, okay, multiplied by, well, I should really put E0 here, because I called it E0. It's really E0. E0 multiplied by D minus T, so that will give me these two spaces. And then E over kappa, which is the electric field, this guy, multiplied by the thickness D. And if I pull E out, then I get T minus D and T over kappa from here. That means, again, if I pull T out from these two guys, I get 1 over kappa over there. And I want C, so C is equal to Q over delta V, which is Q over E, and remember it's 1 over delta V, so that means what? That means it's, if you do all of this, it's simply kappa multiplied by T minus t plus t divided by kappa. So this will be kappa multiplied by t minus d multiplied by kappa plus t. Okay. So that's that. Now, if you substitute for the electric field as Q over epsilon A, that's the electric field, this electric field, which I called it E0, all of these E, they should be E0. Then, if I substitute that in here for the electric field, Q will go with Q, and epsilon A will be on top, and therefore C will be this. Okay. Now, the first question he is asking me, what happens if t is equal to 0? What happens to C if t is equal to 0? If t is equal to 0, that means this guy does not exist. So I should get that the answer I should get, it should be epsilon A divided by d. Okay, so let's check that. If I substitute with t is equal to 0, this will go, and kappa will cancel with this kappa, and then again we get epsilon A divided by d, which is exactly what I expected. Second, what happens if kappa goes to 1? That means it's air, right? If it is air, that means it's just like this guy, this kappa is equal to this kappa. That means it simply go back to the same value epsilon A over d. Okay, so if kappa is equal to 1, so this is kappa, and this kappa is equal to 1, so I have d minus t plus t, so these guys will cancel, and this will be 1, so I get epsilon over d, and these guys are the same. So whether t goes to 0 or kappa goes to 1, it's basically this guy does not exist there. Now, the third part, what happens if t goes to d? If t goes to d, that means the space in between these two guys is filled by the dielectric material. That means it's going to be C multiplied by kappa. Let's see it. So if t goes to d, so that means I'm going to substitute for t as d. D minus d is 0. And so this will cancel, this will go, and then I have epsilon A kappa divided by d, and that's what I have there, and the problem is solved. All right. Next example, it's a little bit different. So now I have a dielectric material or a parallel plate capacitor, and I inserted two dielectric materials, half. Each one of them fills half of the capacitor or the parallel plate capacitor. And so the area, this will be area over 2, this will be area over 2. And the separation is the same for all. Compute the capacitance of the system or the equivalent capacitor. Now, what is this? The way this should be or should look like is simply it's a parallel combination, except now I have kappa 1, kappa 2, and this area is half A, and this area is half A, and D is the same. So since they're parallel, so simply you add, so C equivalent will be C1 plus C2, and C1 will be simply kappa 1, epsilon 1, and area over 2 divided by D. So this is simply kappa multiplied by C. And this is again kappa 2 multiplied by C, except the area is divided, is half of the area. If I pull all of this part from both sides, so this one and this one here, if I pull it as common factor and the 2 goes here, then I have epsilon A kappa 1 plus kappa 2, and that's the equivalent capacitor capacitance for the two for the combination. Okay, second, example 15. So what happens if I have these guys stacked on top of each other? And he wants you to calculate the the equivalent capacitance for this combination. Well, this is what it looks like: kappa 1, kappa 2, kappa 3. Now the area is still the same, but the distance is divided into 3. So this will be d over 3, d over 3, d over 3. And I have a parallel combination, series combination. If I have a series combination, then 1 over C equivalent will be 1 over C1 plus 1 over C2 plus 1 over C3. And remember, C is there is a this is kappa 1. This would be 1, 2, 3. Okay, so kappa 1 epsilon A d over 3. So when I do this, will go here. Okay, and the d will go here. Yeah, again, same thing. The 3 will go here, and and the D will go here. And so if I do that, then will be D over 3 kappa 1 epsilon 1a. And as you can see, this is a common factor to all three. So if I pull that out, D over 3 epsilon a, then I have 1 over kappa 1 plus 1 over kappa 2 plus 1 over kappa 3. The common factor for all three, kappa 1, kappa 2, kappa 3. So it will be kappa 2. Oh, sorry, this is kappa 1, kappa 2, kappa 3. So it will be this, remember, kappa 2, kappa 1. This is a little bit here. It's so this will be kappa 2, kappa 3, and then kappa 1, kappa 2, and this will be kappa 1, sorry, kappa 3, kappa 2. So when I flip it over, it will be this. Remember this again. There is a mistake here. You have to. So this is kappa 2, kappa 3, and this will be kappa 1, kappa 3, and this will be kappa 1, kappa 2. Okay, that's the solution. I forgot to, because this is when you take this as kappa 1, kappa 2, kappa 3 divided by this, you get kappa 2, kappa 3, and here you get kappa 2, kappa 3, and here you get kappa 1, kappa 2. Okay, so then he said, okay, what happens if kappa goes to 1? If kappa goes to 1, in all three of them, then this will be 1 times 1 times 1, and this 1 times 1, 1 times 1, 1 times 1. So this will be 3, and this will be 3. So that, what does that mean? That means when kappa goes to 1, just like you have an air in between them, and you don't have these dielectric materials all together, and that means simply the combination will be the initial capacitance, which is epsilon A over D. And that's what we end up getting. We've done this in class, but we'll do it very quickly. So what we have a parallel plate capacitor that has a capacitance of 112 picofarads and a plate area of 96.5 centimeters, and there is a dielectric material, mica kappa 5.4, and then when we turn the voltage difference of 55, he wants you to calculate the electric field and then calculate the magnitude of the charge. So using these formula here, use a formula which we know, so C, which is epsilon over A, and we can get D from this formula here. So D is V over E, right? And then of course E will go up, and then I have C is epsilon A over E0. Okay, so he gave me C, I have C, and he gave me the area, I have it, and he gave me V, and epsilon is known. So from here I can get E0, which is simply equal to VC divided by, so I can get the electric field from this, which is, as you can see, now this is the electric field, and if I want the electric field when the dielectric is inserted, all I have to do is just divide by kappa. The second part, he wants to find the magnitude of the charge on the plates, and of course, since I know the electric field is equal to Q divided by epsilon A, and it's divided by kappa because it's reduced, from there I can find the charge, which is simply, it will be epsilon A kappa multiplied by the electric field. Okay, the last question, which again I explained in class, and I'm going to leave this as homework. The only challenge in here, which you need to know, is that in the first part, all you have to do is that you start with these two guys are series, and these two guys are series because he wants to know what's the equivalent capacitance of the group C1, C2. So C1, C2, you can do that. And when you say what is the charge on each capacitor when it's open, so you have to calculate that. You know, the voltage here What's the voltage? The voltage difference is 12. So the voltage difference here is 12, and the voltage here is 12. So when you calculate these guys in series, so it will be 1 over what's C1? C1 is 1 plus 1 over C2, which is equal to 3 over half. So C equivalent will be 2 over 3, and from there you can calculate the C equivalent, and that will give you Q for these guys, which is the same for both guys, and the voltage here will be the same as this voltage, and you can find the combination. Again, you can find the capacitance for this, the total capacitance and the total charge and everything, just like what we did before. The challenge is, it's what happened when you close this. Okay, and as I said in class, when you close it, all it happens is that you're going to have something like this. Okay, so these capacitors, you have to first look at these two as connected in parallel. Okay, and these two connected in parallel. Before these two connected in series and these connected in series, but now it's closed, so you have to do this and do the same thing. Find the charge on each capacitor, just like what we had before. It's a little bit long, but it's very interesting. And that's it. So this is the end of the this chapter on capacitors, capacitance, and dielectrics. And I think we covered everything. The only thing that you need to do is just review this, and I made sure that we have enough material for you in the in this sort of in these two videos, enough for you to. All right. So we'll see you in class. Thank you very much.